Hello everyone, my name is Giorgi Vacheishvilli and I am a master student in biomedical engineering at the University of Kragujevac, Serbia. Today I am thrilled to present my research on the usage of rotary wall vessel to aggregate 3D cell cultures. A cutting-edge technique shaped the future of tissue engineering and regenerative medicine. Three-dimensional 3D cell cultures are revolutionizing the way we study biology and medicine. Unlike conventional 2D cultures, 3D systems allow cells to grow in all three spatial dimensions, mimicking the structure and behavior of real tissues. This physiological relevance is critical for areas like tissue engineering, drug discovery, and cancer research, as it enables the development of more accurate models of human biology. However, 3D cultures are not without their challenges. Traditional methods, such as static or spinner flask cultures, often face limitations, such as shear stress can damage cells, nutrient and oxygen distribution can be uneven, cell aggregates often lack uniformity in size and structure. This is where the Rotary's wall vessel bioreactor comes into play, offering a dynamic and low shear environment for growing 3D cell aggregates. The rotary wall vessel bioreactor, initially developed by NASA, is an innovative tool designed to simulate microgravity on Earth. By rotating a cylindrical culture chamber horizontally, the system balances centrifugal and gravitational forces, creating a near weightless environment. This prevents cells from settling and encourages free floating growth. This unique design minimizes shear stress, enhances nutrient diffusion, and promotes formation of uniform spheroids or organoids. Uh, rota- Rotation wall vessel systems offer several advantages that make them superior to traditional 3D culture methods. Firstly, reduced shear stress. This minimizes cellular damage, ensuring higher viability. Secondly, uniform spheroid formation. Cells aggregate more evenly, creating structures that closely mimic in vivo tissues. And last but not the least, enhanced diffusion. Continuous rotation improves the distribution of nutrients and oxygen, addressing a common limitation in static cultures. One of the most promising applications of rotary wall vessel bioreactors is in tissue engineering, particularly for cartilage and bone regeneration. Cartilage engineering. Chondrocytes grown in rotary wall vessel systems show enhanced extracellular matrix production, including collagen II and glycosaminoglycans, which are crucial for functional cartilage repair. As for bone regeneration, osteoblasts cultured in these bioreactors demonstrate improved mineralization and osteogenic gene expression. For example, studies using rotary wall vessel bioreactors have shown that viable, dense cartilage-like tissues can be generated within 14 days without requiring scaffolds or microcarriers. Now moving on to contributions to cancer research. Rotary wall vessel bioreactors are also invaluable in cancer research. They enable the creation of tumor spheroids that replicate key features of solid tumors, such as hypoxia gradients, cell-cell communication, and drug resistance mechanisms. These tumor spheroids are ideal for testing anti-cancer drugs as they better reflect in vivo drug penetration and response compared to traditional 2D models. Now moving on to role in virus-host interaction studies. Rotary wall vessel bioreactors also provide unique opportunities to study virus-host interactions. Cells cultured in these bioreactors form polarized 3D structures with tight junctions, microvilli, and mucus secretion, features critical for studying respiratory viruses such as RSV and PIV3. As for stem cell research and organized, in stem cell research, rotary wall vessel systems facilitate the formation of embryonic bodies and enhance mesenchymal stem cell differentiation. They are also instrumental in developing organoids, such as neural organoids and gastrointestinal organoids. Neural organoids for studying brain development and neurotoxicity, and gastrointestinal organoids for modeling intestinal functions and diseases. Now, last but not least, we should address challenges and limitations of rotary uh, the rotary wall vessel bioreactor and also its future directions. Despite their many advantages, rotary wall vessel bioreactors have some challenges. For example, complex operation. A steep learning curve makes them less accessible to beginners. Additionally, scalability is a problem. Expanding rotary wall vessel systems for industrial use remains costly and technically demanding. Standardization issues are also a problem. Variations in bioreactor design and protocols can lead to inconsistent results. Now, to discuss the future directions, to overcome these challenges that I mentioned above, researchers are exploring several exciting advancements. For example, integrating the rotary wall vessels with 3D bioprinting. Combining the vessel bioreactors with bioprinting technologies could enhance scaffold based tissue engineering. Real time monitoring is also a good direction to take in the future. Sensors for pH, oxygen, and metabolic activity will allow dynamic adjustments to culture conditions. Last but not the least, extending rotary wall vessel applications to true microgravity environments could reveal insights critical for regenerative medicine and space exploration. So, more research can be conducted in space. In conclusion, the rotary wall vessel bioreactor is a groundbreaking platform for generating physiologically relevant 3D cell cultures. Its ability to mimic microgravity conditions makes it indispensable for applications in tissue engineering, cancer research, and regenerative medicine. While challenges like scalability and standardization remain, ongoing innovations will expand its impact, paving the way for breakthroughs in personalized medicine and therapeutic development. Thank you for your time and attention. Goodbye.